Each of these expressions is an infinite series. They are infinite power series because they have a variable. In this case, the variable is x. They are both forms of a general power series. They are really the two major forms of a power series. The first one is a power series that is what we say centered at 0. More on that to come. So this power series goes from n equals 0 to infinity, some constant times x to the n. The second one also goes from n equals 0 to infinity of some constant x minus a to the power of n. These are power series. These are infinite series. Then the most amazing part of the unit. This is crazy. F of x, now as long as f has continuous derivatives of all orders. Now what does that mean? Well, it has a first derivative and a second derivative and a third derivative, etc., etc. Then f of x can be written as follows. F of 0 plus f prime at 0 times x plus f double prime of 0, x to the power of 2 over 2 factorial, plus f triple prime of 0, x to the power of 3 over 3 factorial, plus dot dot dot, plus the nth derivative at 0, x to the power of n over n factorial, plus dot dot dot. Whoa, this is awesome. F of x, when centered at 0, can be written in this form. Of course, 0 has to be in the domain, and the nth order of all derivatives, the order of all derivatives must exist. Wow, this is amazing. A similar form would be if we centered it at a. Then the function would be f of a plus f prime at a times x minus a plus the second derivative of a times x minus a to the power of 2 over 2 factorial plus dot 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 plus the nth derivative at a, x minus a to the power of n over n factorial plus dot dot dot. Wow, these are amazing. The point of this unit, the point of this lesson, is to create power series. And we're going to use the things that you see on the screen now to do that. Now, in this lesson, we're going to look at 4 ways, A, B, C, and D, 4 ways to make a power series for some functions. A geometric sum is actually a review of the last unit. Then we're going to raw construct, we're going to manipulate known, and we're going to substitute into known. As a result of doing these in the lesson, we're going to compile a list of known series, power series. Let's start with the first one, and we're in part A of geometric. We look at this function and we say to ourselves, wow, this looks a lot like the sum of a geometric, where a1, the first term, is equal to 1, and the common ratio is equal to x. That being the case, I can write out the terms of the geometric, 1 plus x squared plus dot 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 plus x to the power of n plus dot dot dot. So we've successfully made a power series for the function f of x, but we also want to mention the interval of convergence. This is true only on a certain interval, and we know it's only true when the common ratio, in this case the common ratio x, is less than 1. It's the only way that this will converge, and that leads to the interval of convergence -1 to 1, not including the endpoints. And we can, of course, summarize using sigma notation, and we can say from n equals 0 to infinity x to the power of n. Now let's take a look at the second one. G of x is 1 over 1 minus 2x. At any point that you want to pause and try it, that would be great. Here we also recognize this is the sum of a geometric, where the first term is 1, and the common ratio in this case would be 2x. So now we can write out the terms 1 plus 2x plus 2x squared plus dot 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 plus 2x to the power of n plus dot dot dot. We made a power series for the function g of x. Now it's only going to be true on an interval of convergence when our common ratio is less than 1, which leads to -1/2 is less than x is less than +1/2. Now the center of this interval here is clearly 0, and the center of this interval here is also clearly 0. You will recognize or might notice in each of the series that we have x alone and not a quantity x minus a. I would like to summarize this from n equals 0 to infinity, and we can write this as 2x to the power of n. We could also write it, we have some options, n equals 0 to infinity of 2 to the n x to the n, to summarize the infinite series to represent the function g. Now for the third one, continuing this geometric sum procedure, a1 is 1, but this time you might notice that r is negative x. See, we could write this as 1 over 1 minus a negative x. So with that being the case, we have 1 plus negative x plus negative x squared plus dot dot dot, and I'm going to write this now x, 1 minus x plus positive x squared minus x to the power of 3 plus dot dot dot. Now this will strictly alternate. I'm going to use the alternating indicator as such, and then I'm going to summarize it. -1 to the n x to the n from n equals 0 to infinity. Again, we always have to look at the interval of convergence because it's only true on that interval, and we say for absolute value of -x less than 1, which leads to the same interval of convergence we found for f of x above, which also has a center of 0. And let's see, let's move this up so we can look at the fourth one. The fourth one we're going to call p of x, and p of x is 1 over 1 plus x squared. A1, 1. Common ratio, can you see this? The common ratio is negative x squared. So first term is 1, the next term is negative x squared plus negative x squared squared plus dot dot dot. So we have 1 minus x squared plus x to the power of 4 minus x to the power of 6 plus dot 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 plus -1 to the n, alternating indicator, x to the power of 2 to the power of n, so x to the 2n plus dot dot dot. Summarize. x to the 2n from 0 to infinity. We have to look at the interval of convergence, common ratio less than 1. That will lead to the interval of convergence, -1 less than x less than 1. Again, centered at 0. Now the next one I've made very obvious, h of x, doesn't have to be in this form. H of x could have been written something like 1 over 4 minus x, which isn't quite as obviously geometric. So I've opted to go right to the form here above. Now looking at that, cross this out, looking at that, we can say that a1, the first term, is 1, and the common ratio this time is x minus 3. And the way that I wrote it is indicating something about center, and again, we're going to investigate this fully, but let's look at the terms of this geometric. This is going to be 1 plus quantity x minus 3 plus quantity x minus 3 squared plus dot dot dot, that continues, x minus 3 to the power of n plus dot dot dot. Summarize this, and it's simply x minus 3 to the power of n from 0 to infinity. We will look at the interval of convergence, and that's when common ratio is less than 1. If you stop right now, you can see that the center will be 3 and the radius will be 1, and when we write it out fully, simplify here, so this is going to be 2 is less than x is less than 4. So we can see that the center is no longer 0, but the center in this case is 3, and that is also expressed in the form that I wrote it, in my summary form, and in the form here I am showing it written in terms of its center.